Now in this session we start on the formal definition of a Turing machine. Now we've done this kind of thing before. We did it with a formal definition of the finite automaton. So we had some kind of tuple. I think the finite automaton was a 5-tuple. And then we did something similar, a formal definition of the PDA, push-down automaton. That was a 6-tuple. We added an extra alphabet. We had one alphabet for the input stream, and we had a separate alphabet, a set of allowed symbols, labeled capital gamma, remember? And that was the so-called stack alphabet. It was the allowed symbols for the stack that you could push and pop on the stack. And we'll do something similar now for the TM, the Turing machine. And it, as I mentioned before in earlier sessions, it will be a 7-tuple. So we will need 7. We need to specify 7 things in the list of this formal definition of a Turing machine. Now, most of them are pretty much the same as what you've done already. So you should be fairly familiar with this formal definition of a Turing machine. Now, as usual, with any of these machines, any of these models, like this is our third major model we're talking about on this board. First one was finite automaton, second one was PDA, push-down automaton, the stack-based machine, and this third one now, much more powerful, the Turing machine. So in all 3 cases, well, certainly for the first 2, because we haven't done the third one yet, but you are probably aware that the guts, the heart of the formal specification was the transition function, the delta. Okay, the mapping between where the machine is now and what its next move should be, what it should do next. Basically, that's what the transition function does. It transitions, it changes from its current situation to the next situation, speaking broadly. Okay, and it's no different for the Turing machine. It's the same. All right. So let's see. Now, what we did the previous session with the snapshots, that gave you a feel. So you probably got an idea now. Like if this whole Turing machine stuff is new to you, you probably have at least a feel now, an inkling of what it is and how it works. So what we've done so far is really just a sketch, right? It's not, the full details are not there. To get the full details of what a Turing machine can do, like everything, I don't mean that it can do everything, but all the details of how it functions, you need a formal definition. Okay, so we've just sketched how it does, how it functions, but we haven't given all the details. So to get the complete description of what's going on, how a Turing machine functions, then you need the formal description. You need this 7-tuple, as I'll get onto in a moment. Right? Now, as usual, a formal description. This 7-tuple, it describes the parts of the machine. These 7 things. What else? Oh, now here's an interesting remark. In practice, not in theory, in practice, in reality, usually a full description of a Turing machine is not given. Why? Because it's not practical. There's just too many details. It's too involved. Right? It's too long. Like the formal description is actually very large. And you'll see why with a bit of experience once you start playing with, actually programming. I mean, it can get quite creative. Like typically when I was teaching this course to a class, when I was a wage prof, a classroom professor. Remember that old technology? I'd set my students the task of actually programming a Turing machine. Well, you can't see it, but well, maybe the bottom line here. But designing the transition rules, the transition function, if you like, in such a way that your Turing machine performs a certain task. In the case we're talking about with machine M1, the task was to see whether the binary strings either side of the hash were identical. Okay, that's a particular type of task Turing machine could do. And in effect, you have to write a program. You have to write the transition rules to allow that to occur. And it was probably that, more than anything, that inspired people to consider the possibility of using the technology of the time, electronic valves, to actually implement a Turing machine. Well, more efficient. Turing machine, very inefficient. But the idea of a programmable and general purpose machine, but again, getting a bit ahead. Can't talk about general purpose machines yet until we understand the concept of a universal Turing machine. But we're getting there. But that's next chapter. Okay, so we're talking about the formal definition of a Turing machine. Now, in practice, they're rarely given, and the bottleneck, the problem is the delta, is specifying all the transition rules, because there are a lot of them, often. Okay. So, but the delta, your transition function, the thing that the function that maps from, well, here we're getting into the guts of it now. I've put a big rectangle around it because it's sort of the essence of a Turing machine. So, what's going on now? Look, this is just abstract math, right? As it's presented. So, you're talking about a Cartesian product or cross product of two sets. Here's like a double cross product, or a Cartesian product of three sets, so two x's. And so your Q, your gamma, and this set here, LR, they are just finite sets, okay, and from a mathematical perspective. But physically, in computer terms, if you like, what's going on? Well, what it's saying is, well, I've said it in words previous session, your machine, imagine you are the machine, you're the TM, okay, and you look at your current state, say it's a little q, so that little q would be a member of this set big Q. Q, as usual, it's just the set of states of the machine, nothing new there, right? And your gamma here, capital gamma, that's a set of symbols that can be on your tape. So you now, a member of this Cartesian product is an ordered pair. Remember, and the first member of the pair is a particular state, and the second member of the pair is a particular symbol contained on the square that the read-write head is currently positioned at. Okay, so let's call that little a. Let's say the symbol currently being read on the tape by the read-write head is little a. So let's say it's in your machine. You're the machine. You are in state little q, and you're reading little a. Let's say. Okay, you consult you plug those two variables into the transition function. So you'd write them in. So the current state and the current symbol being read, put those in the form of an ordered pair. So little q comma little a, and then look in the transition function. So that would be your input, your member of this set, and it will map it to a member of this set. And how do you, now you need to interpret this, right? This is a triple product. It's a Cartesian product of three sets, So the members of this set, remember a Cartesian product gives you a set, results in a set. So the members of this set